Okay, so I wanted to give you all a little introduction to Chapter 8. Go through the material a little bit so you have something to go with before we talk about it in class. So we talked about how having a metabolism is one of the characteristics of living things. So in this Chapter 8, we want to talk about metabolism in a bit more detail, which will lead us into Chapter 9, which is cellular respiration, Chapter 10, which is photosynthesis. These three chapters, 8, 9, and 10, will be considered a single unit. So with your metabolism, as we talked about earlier, it's basically you can define it as the sum total of all the reactions going on inside of you. And so these reactions, as we'll see, basically occur in metabolic pathways. So you're attempting to take some substrate, some starting molecule, and converting it into a sequence of different products until you finally get to the product that you want. And you have an enzyme involved with facilitating each of those reactions. And so these all would be considered part of the metabolism. These pathways, as I point out in the book, can be of a couple different flavors, if you will. They can be, whoops, I misspelled that. They can be catabolic and anabolic. And with catabolic, this is where you're basically breaking something down. You're taking a larger molecule and breaking it down into smaller molecules. We'll see how cellular respiration is a great example of this. Anabolic is where you're taking smaller molecules and building up larger ones. Photosynthesis being a good example there. I find it easy to remember these because if you're familiar with the term anabolic steroids, these are the steroids that people take to build muscle mass. So anabolic steroids are to build up muscle mass. Okay, so with your metabolism, energy is extremely important. And so you all are familiar with the idea of kinetic and potential energy. And you know that an object at rest has a certain potential energy, and if that object were to fall off the desk or roll down a hill, it's basically some of that potential energy is being converted into kinetic energy. Now, with metabolism, biochemical pathways, we're mostly going to be focusing on what we could call chemical energy. That is the energy inherent in atoms and the bonds between atoms. And we'll see that by breaking these bonds in catabolic reactions, we can release energy. In building up these bonds and making larger molecules, we can put energy into molecules in anabolic reactions. And also, heat is going to be really important, or thermal energy is part of our metabolism. Heat essentially being the energy that's given off by objects due largely to the vibration of the atoms within that object. So it's that energy given off that can be measured basically as temperature. Okay, so there are a couple laws of nature that constrain living things in metabolic pathways. And this is the first and second law of thermodynamics, and you might be familiar with these. The first saying that essentially the amount of energy in the universe is fixed. Okay. And the second saying that when energy, here in the case of this chemical energy in this fish that this bear is eating, when that energy is converted into a different form, here some of that energy is being used in the movement of this bear, that the conversion is, you might say, not terribly efficient. Or in the process of converting that chemical energy into basically motion, you give off a lot of heat. This warm-blooded animal has a high metabolism and gives off lots of heat, so that chemical energy is basically converted into what we might call less ordered forms of energy. A fancy way of saying this is that entropy or disorder has increased. You've gone from a more orderly form of energy to a less orderly, more diffuse form of energy, and that's sort of the way in which nature operates. That is, entropy tends to increase. Things tend to go from a more ordered state to a less ordered state, from low entropy to high entropy. Now, so I just said that entropy tends to increase in the universe, but of course living things have a lot of order to them, and they're able to take less orderly things like carbon dioxide and water, and through the process of photosynthesis able to convert these less orderly things into a higher state of order, taking carbon dioxide and water and producing some glucose, a more complex molecule that has essentially less entropy. Now this is interesting because we say the universe likes to go to a more disordered state. Well, this is an interesting thing about life, is that life is essentially able to take simple things and make more complex things. Now, as the book points out, and I would direct you to recheck this out, it's on that last section on page 145. This does not disobey the second law of thermodynamics, because, as is pointed out in the book, essentially, as a whole, entropy is increasing in the universe. All life does is sort of temporarily reverse that in a particular organism. And again, it is temporary. Okay, so that's section 1. Let's look at section 2 here. Alright, so now we need to talk about this thing known as free energy. So, free energy is essentially, you can define it as sort of the energy that's available to do work. And you may have recalled from middle school or freshman biology or wherever that we sometimes describe energy as that which is available to cause to cause change or do work. Now, as the laws of thermodynamics, particularly the second law of thermodynamics, points out, not all of the energy that's in something is going to be used to do useful work. Some of it essentially is wasted. Okay, it's given off as heat. So the free energy is that which is really available to do some work for us. All right. So these cartoonish examples here show how essentially this person has taken the effort to climb up to this high dive. It's taken energy to do that. They jump off, and basically some of that energy is then turned into kinetic energy. And so the amount of free energy described as G, or the change in energy, has decreased because some of the energy has been released from the system. The same when these molecules spread out, or when you take a complex molecule and break it apart. There has been essentially energy released during this process, and so the amount of energy available to do work is less after you start. Okay, so we can think of free energy with this equation. All right. This is on page 146 in your textbook. Okay, and so what is this? So delta G basically represents the change in the amount of free energy. Okay. Delta H, this is the change in the total energy in the system, or what is sometimes called the enthalpy. T is temperature. S stands for entropy. Delta S, change in entropy. Okay. So essentially, the change in free energy is that portion of the energy that comes out of the total, and that portion is a function of how much entropy has changed, and also temperature influences this somewhat. So that after a reaction, particularly an exergonic reaction, we've got, this amount of energy in our reactants. After we carry out the reaction, we have a lot less energy in those products. That is, energy has been released from the system. So that means that in these products you have a lower free energy than in the reactants. There's been a change in it, and it's been released. So now it's decreased. On the other side, with an endergonic reaction, you start at a relatively low amount of free energy, but now, because you've done this, why won't that stay? I don't know. There we go. Because of this endergonic reaction, you now have increased the amount of free energy in the system. Okay. So, depending on the type of reaction, free energy, the amount of energy can be released, or energy can be taken in. Free energy can decrease or increase. And this is the analogy we're given in our book, sort of a water wheel, if you will. And so up here, you've got on one side of the system this water that's higher. It flows downhill, turns this wheel, lights the light bulb. But then eventually, the water gets down to such a level that you're no longer turning the wheel. You're basically at equilibrium. Okay. At this point, you've reached equilibrium. There is no change in free energy at all. You've reached a stable situation, equilibrium. Whereas while the system is running, we're giving off free energy. We're releasing it. Delta G less than 0. All right. Now, if you keep a constant flow of water in there, you can keep the system in a state of disequilibrium such that delta G energy is always being released from the system. And of course, that's how hydroelectric dams work. You constantly have water flowing through the dam to run the turbines. Now, with living things, reaching equilibrium in terms of your metabolic processes is not a good thing, because you're constantly needing to process food and extract energy from it and do work in your cells around your body. So we have this analogy here, in which we have a constant supply of input of materials containing energy, nutrients, etc. And you end up with waste products out, but along the way, that energy, those materials are used to do work in a series of steps in a metabolic pathway that is sort of in a constant state of disequilibrium, in which the energy from one step is often used to do some kind of work. Now, sometimes that energy is just given off as heat to keep your body warm, but a lot of times it's there to do other kinds of work, to facilitate some kind of other chemical reaction. All right, I want to stop here with section 2, and I'll do some of the others in another video.